All right, so we had talked about radio telescopes last couple of our little mini lectures. And the key here towards the end was not just radio telescopes, but having an array of radio telescopes. Because an array of radio telescopes lets you use the idea of constructive and destructive interference. And so you can have, for example, interferometers and the very large array with computer processing and so forth. You can actually make an image, not just measure signal from space, but actually make an image, a radio telescope image. Okay. So the next question, though, would be if radio telescopes can be put together to simulate a very large telescope, could it be possible to do optical interferometers? Because after all, that would simulate a much larger telescope than just one telescope. So that'd be what we want to do. And so problem is that in order to do the interference, you have to know you got to have the one telescope to another telescope. You got to know the position between the two telescopes to within a fraction of a wavelength. Well, if radio waves are going to be, this long, you need to know the center of one telescope to the other by about to within a few inches. If you have radio waves that are going to be, like 20 centimeters long, you just need to know within about 4 inches where one telescope is to another telescope. Now, that can be done. It's tough, but it can be done. But if you're using optical telescopes, this is a lot tougher. You got to know the center of one telescope to the center of another telescope to within maybe 1/20th of the diameter of a bacteria. And that's way tougher to do. For radio telescopes, you can do this with radio telescopes that are pretty far apart. For optical telescopes, they actually have to be so close together you can actually fire a laser between them and use the laser and interference of the laser itself to measure that distance to that level of precision. So that means that you are limited to much closer instruments. And it's much harder to make that work. Well, guess what? We have made it work, though. The Keck telescope. We have Keck 1 and Keck 2. Now, Keck 1 can look at something, and Keck 2 can look at something else. And that's no problem. So you can have two of these giant telescopes looking at things. Or you could have something up here, and Keck 1 and Keck 2 look at the same object. And now the light of one of them can be fed underground, and light of the other one fed underground and then put together in the laboratory underneath. And now you have an optical interferometer that simulates, each one of these is a monster telescope, and now you can simulate the resolution of a telescope that big. And so that's going to be much, much, much better. It doesn't work all the time. Most of the time, you're actually going to use each telescope as an individual telescope, but once in a while, you can throw them together and get much, much higher resolution if you need it. Well, in South America, the European Southern Observatory has built a facility that is 4 individual telescopes that strung together can simulate one very large telescope. So what would we call such a facility? Well, the Very Large Telescope. Okay, and so remember, it's astronomers naming stuff. And so, so the Very Large Telescope is actually 4 different telescopes that can look at 4 different things, or they can all look at the same thing and simulate one very large telescope. And so that's that. In fact, they've actually added a couple outrigger telescopes out here that actually simulate even slightly larger. So that's an example of an optical interferometer. The Large Binocular Telescope in Arizona is another example of an optical interferometer. So here it is being constructed right here, and there's the facility right here where it's being built. And so it's going to act like, even though you have two mirrors here, it's going to act like one big telescope of that size right there. Okay, so again, this is an example of optical interferometers. Now, the Keck is a good example. But what we would really like to do is have like a fleet of space-based telescopes that can be stretched out over miles. Imagine you got laser links between them all, so you know the exact position of all in a fraction, tiny fraction of a millimeter, a fraction of a nanometer even. So we're trying to find out, use that, and then that would actually allow us to simulate maybe an optical telescope that is miles across, or maybe even hundreds of miles across. Such an instrument using optical light could actually resolve a planet around another star and resolve it clearly enough you could actually see if there's continents on it, and maybe if those continents have evidence of greenery indicating life. And so that would be, in fact, NASA's been talking about building something called the Terrestrial Planet Finder, which is a very large space-based interferometer, but they've never been approved money to do that. But that would be the capabilities of such a space-based interferometer. So that's kind of what we're looking at into the future, to supplement our other space-based telescopes. So with this kind of gets to the end of what we were talking about with telescopes. Just tie it off here with space-based interferometers. So now we've talked about light and the physics of light. We've talked about telescopes and the basics of how telescopes work. So now we get back to talking about stars again. Now that we talk about the instruments, we talk about the spectrum of stars, we're ready to actually now go back, spectrum and how you measure all this stuff. We're now able to go back to stars, talk about the spectrum of stars and how we actually know what we know about stars. So that's going to be the next set of topics, is back to stars again, after we had this little interlude on these other sort of topics.